Hi, everybody. I'm Hamid, a mechanical engineering PhD student coming from Tehran, a city with 15 million people population. So born and raised in that city, I saw how the pollutant changed the color, sky color from blue into a gray one, and making lots of, troubles for people, especially for elder people and also children's. But this is some part of the environmental issues that we are dealing with currently. On the other side, we know that we have limited resources, that we are responsible for that, and we need to preserve some part of that for our next generations. For me, as a technical person, as an engineer, the answer for these problems are summarized in two words: clean and sustainable energy. That has different types, including biofuels, geothermal, hydroelectricity, solar panels, and wind energy. Out of which, as a mechanical engineer, I'm interested in windmills. Because of having lots of, moving components, I felt that there's enough, lots of opportunity in this field for me to be innovative and a helpful person for my society. So the wind energy has positive and negative side. It is the largest new energy as of 2017. It is avoiding emission lots of CO2 and also saving water consumption, approximately 300 gallons per person during the 2017 in the US. And it's creating jobs. But it has negative side. It needs to be cost competitive with other resources. It has transportation issues. Just right now, based on the news, we have transportation issues from Hamburg to the Arkwright. And also, some people don't like it. They say, not in my backyard. So we thought that how we can, tackle these issues. So we thought about an innovative design for wind turbine blade. If you look at the wind turbine blade cross section, it is twisted. It's not straight. This twist is to increase its aerodynamic efficiency. The twist is, however, optimal just for one wind speed, while we know that the wind speed changes, constantly. So we thought that what if we have a blade that is, adjusting its twist as the wind speed changes? It seems cool, right? Like a giant robot that is twisting its arms. It is cool, but it is so challenging for engineers and designers. You need to have special specifications in your, structure that could be easily twisted to minimize actuation energy, while it needs to keep its aerodynamic shape, So, to target these issues, we thought about an state-of-the-art manufacturing technique to reach out this smart structure. And that is where additive manufacturing comes together with our design for the wind turbine blade. It has lots of advantages. It is capable of creating complicated geometries, and also it has directional properties that we are looking for. However, additive manufacturing is not yet evolved enough to create 80-meter long blades. But we can use still its advantages by modifying our design. So we came up with this. Using additive manufacturing, we came up with a design, and we think that eventually we would be able to build our blades on the installation side. That'd be great. The shipment problem would be solved totally. We would be able to customize our blades based on the installation side, while the current ones are not. And we will be able to have recyclable blades, But as I said, we need to modify our design. So we came up with this design: a modular blade, including central spar and 3D printed segments that are mounting on these blade and being covered by non-structural skin. So we believe that this blade will increase the efficiency and will allow the turbines to work in lower wind speed, and as a result, to bring the electricity into low wind rural areas. It will also resolve some part of the transportation issue and will help us to drop the cost. To approach such a blade is a multidisciplinary work. It needs to work on the aerodynamic design of the blade. It needs structural design and control, and also it needs to be manufactured. There's no point if it designed a great and optimal blade that has highest possible efficiency, but it couldn't be manufactured. So all of these are interrelated to each other. They are imposing restrictions on each other. So we need to study every single of these aspects. We start our study with aerodynamic analysis. Our case study on a 13-meter blade showed we can increase the efficiency by up to 13%. But this is not the end of the story. Flexible blades carrying the less load, they can reduce the fatigue loads by more than 70%. And by that reason, we can install larger blades on our wind turbines, and as a result, create more electricity by up to 11% more than the regular ones. Also, our structural simulation showed that our suggested design is capable of creating the required optimal shape as the wind speed changes. We have also worked on the control framework, how to change and adjust the twist as the wind speed is changing. Currently, we have a group of 4 students, including 2 PhD and 2 master's students. And in some part, we are working on saving material by distributing the material more optimally inside of the structure. And on the other side, we are testing additively manufactured carbon fiber samples to simulate their behavior more realistically. We believe this project will not only affect the wind energy, but also it will help us to save material and resources in other other components that will be manufactured by additive manufacturing by distributing the materials more wisely. Thank you. And I need to say thank you for the UB sustainability.
All right, thank you. Any questions from our judges?
Okay, I'm just gonna formulate it quickly. So you laid out a few objective challenges. I think you actually had 6 in that slide, 6 different objectives that your design might, 6 different challenges that wind turbines face or the industry faces. I'm curious. There was a slide that had 6 sort of points all the way about the challenges that you started.
Okay.
Yeah. So you talked about like that bottom right corner there, the NIMBYs, right? Who are concerned about things like sound and what it looks like, and it's on my property. What does your design do to address that?
We haven't yet focused on the design, but we hope that at least regarding the efficiency-wise, if the cost drop, we believe some part of those people will like wind energy. Okay. And the other thing is that this color, this right side, they are not actually challenged. They're the green side, they're positive sides. And the red part is kind of, negative side.
Got it, thank you.
Yeah, sure.
Hi, thank you for your presentation. A quick question, sort of related question, I suppose, is that a lot of the future of wind development, at least in the Northeast, will be offshore in a corridor that sort of runs along the sort of mid-Atlantic up until about the Boston area. Do you see application for this? I know you talked about low wind speeds, but have you thought about sort of higher wind velocity speeds? Some of the transportation issues in particular present real big problems for your traditional windmill blades and all that jazz. So I'm just thinking about application in varying wind speeds and sort of other installation areas.
Okay, by low wind speed, I mean that increased efficiency will allow us to use low wind speed as well.
Sure.
But we are working on all, possible aspects, especially the large ones. And there's some other details that, because of the limitation in the time, I couldn't bring it out. But we are going to work on the vibration of.
So just a quick, so maybe to point the question a little bit, do you think that in a higher wind speed, let's say, for example, off the coast of Long Island, for example, where a very large wind installation is being planned for by New York State, this the rearticulation of the wind blade would increase the efficiency of large windmill installations as well? Or I'm thinking about, I guess my question is, does this innovation amplify the existing efficiencies of other large wind blades as well, as opposed to just simply creating space for?
Yes, it does, and that's the point that increasing efficiency is not so much high because they are going close to being mature. Okay, they're pre-developed, But in those large turbines, besides the efficiency, even more important than that is the fatigue loading. And the flexible blade is capable of reducing the fatigue loading up to 70%.
Okay.
Okay, and that's
There you go.
another thing. It's called in the renewable wind energy. It's called region 3, where we have more than we need. So on that case, we are trying to stop turbining efficiency. We are trying to keep it, not to produce more than we require. And that's the place that the loading is important. And we are working just right now by keeping the same power, reduce the loading.
Yeah, how you doing? Just real quick, adding on a little bit to Eric's question. Wind turbines have a lot of moving parts to begin with. The type of design you have is very interesting, but I'm wondering if you could speak a little bit about how you balance the efficiencies gained with reliability issues that may come into play with the additional moving parts, especially given that some of them may be located, at difficult places to service offshore, that type of thing.
Okay, that's a great question. So this design is both, good points, and the other thing, I'm not going to say negative points, but some points that you need to think about it. So the good point is that by this modular design, if there's any erosion or whatever, the maintenance would be, less time consuming and easier by just changing that module, okay? But on the other side, you're right, we need to, see how much, energy it's required and how it is, behaving against the fatigue. And that's why it's going on just right now on our test, We are trying to find additively manufactured carbon fiber components. Okay, there's not enough data outside for these kind of materials yet. And for that purpose, we have bought a great printer that is using continuous fibers. It's just one type in the industry that is using that. So there's no data on that. And we are trying to see how these materials are behaving, so we can simulate exactly what's going on regarding the deformation, required torque, and also fatigue loading.
So for the pointedly, you haven't done a wear and tear study on any of the two pieces yet, on the moving parts yet, right?
We haven't done the detailed design. We have done kind of framework till now. So I said it's really broad work. So we started our design exploration from aerodynamic going downward.
One more follow-up question.
Mhm.
Have you modeled any production? Have you run production models on any of the ideas? Let's say, for example, a NIMBY spot, let's say in Allegheny County.
Okay.
Hypothetical.
Not on this size. Till now we have had 2 case studies because wind turbines you need to have reliable data for them so you can get reliable answers. On the National Renewable Energy Lab, database, there were several blades, so we are picking from those kinds that they have been validated, so you're sure that your results are valid. And we started from a small blade, and we are increasing the size. I mentioned the 13-meter blades, but the next step would be 1.5 megawatt wind turbine that needs to prepare the files for that.